Hello. You should see the desktop. Everything should seem okay now. Only a few people are in class yet. People are still coming in. Does it seem okay? Do you see the desktop? Do you hear me? Okay. All right. Wait a second for a few more people to come in. Okay. Okay. So what we're going to do is a few more examples of Java threads. So what Java threads and the P threads examples. Going to compare a couple more of those, and then we're going to start looking at the race conditions. Okay. So let me unzip these. Okay. Let's see. Okay, so here's what we're going to start with. Kind of an interesting little example. Here's something called Orphan thread in C, and then there's an equivalent one in Java. Here's Orphan thread. Okay, so what do we mean by this? Let's look at the C one first. The question here has got to do with what's the role of the main thread? Is the main thread special or not? Okay, in some Java library, I'm sorry, in some thread libraries, the main thread is kind of the dominant thread. And if it exits, all the other threads die with it. In a sense, it's like a parent thread. And if it exits, everything exits with it. On the other hand, in some thread libraries, there's nothing special about the main thread at all. In Java, Java's like the latter. In Java, the main thread's not special at all. If the main thread exits and there are other threads running, the program keeps running. C is a little bit quirky. Yeah, in some sense, you can say C is both ways. You can terminate the main thread and let other threads run, but if you terminate the main thread in a certain way, it takes all the other threads with it. So we want to see how C and Java are a little bit different. And okay, so here's what we're going to do. Here's a main thread, and here's another thread. The other thread just prints the letter A. And the main thread, all it does is it creates the other thread, sleeps for 3 seconds, and then it terminates itself in a variety of ways. So here there's like 4 different ways it can terminate itself. In this case, 3 different ways it can terminate itself, and we're going to use one of those 3. And we'll see that they kind of do different things. The Java version does the same thing. Here's the second thread. Create the second thread here. Let the program sleep for 3 seconds, and then the main thread terminates in a variety of different ways. Okay, so let's go look at this one in particular, the different ways it can terminate. Okay, okay, let me open it in this one, which has got access to the C compiler. So this one can compile the Java programs. This one can compile the C programs. Okay. Here's the key idea. You could exit the thread, exit the program, or return from main. Okay, there's 3 different things you could do there. Exit the thread, exit the program, or return from main. What do those 3 things mean? Okay, exiting the thread just terminates the thread. Now, in this, we'll see that if you terminate the main thread, the other thread keeps on going. This other thread is not affected by the termination of the main thread. But if you exit, now this is actually, see, this is thread exit. This function here is program exit. If you exit the program, that kills every thread. Okay. Okay. So this, no matter where it is in a program, this will kill all the threads because it exits the whole program. But then you can also exit, you can actually return from main. Returning from main has to be there because this is an int function. So if you don't have a return here, it won't compile. Now this is never going to get called because the main thread exits up here. When the main thread exits, it never gets to this line, but the compiler still requires that line to be there because by definition, a function that returns an int must somewhere return an int. Okay. Now, if you comment this out and you hit this, it has the same effect as this one. In the C language, the main method is special. When the main method exits, it exits. When the main method returns, it exits the program. That was designed before threads existed. So that turned out to be kind of not a great design. So you get this variety of things. You could exit the thread, which leaves the other threads running. You could exit the program, and this you can do from anywhere. And if you exit the program, it kills everything. And then you can return from main, but returning from main is equivalent to exiting the program. And it's the only function that does that. Only main, when it returns, will exit the whole program. Okay. So right now, if I leave it like this, when it returns here, it'll kill all the threads. But if you do this, let's watch this. Let's compile this one. Okay. There's a warning because I'm not using the thread parameter here. There's no use of that thread parameter. That's the one warning. Okay. So run this. It's going to run for about 3 seconds. There. See, there's where the main thread exited, and you can see the other thread still running. It'll run forever. But you can see that after about 3 seconds, there's 3 seconds worth of output. The main thread exited and the other thread kept on going. Okay. Now, on the other hand, if I change this to, if I comment out that one and now let the main thread return, now instead of exiting the main thread, I'm going to let the main thread return. As soon as the main thread returned, it took with it the other thread. Okay. Okay. So the reason it's called orphan thread is because this example left you kind of with what you might call an orphan thread. The main thread that started it died, the parent thread died, so the orphan thread is left running. Some threading libraries don't really allow orphan threads, but most do. Okay, so when in this case, when the main thread dies, the other thread runs. And this one here acts just like returning from main. This one but the difference between this exit 0 and return 0 is that exit 0 can be called anywhere in the program. You call it anywhere and it halts the program. Return 0 only halts the program when it's the return for main. You know, it's only main that can halt the program by returning, because main is the start point of the program. Okay, so there's really two cases here. You can exit the main thread, or you could end the main thread. Oh, I have to leave that return in there because it needs to be there, otherwise the compiler complains. So right now this is never going to get called, but if you comment out this, then this one will get executed, and then the thread will return instead of exiting. Okay. Now, what about the Java version? Java is a little bit different, but at the same time, it's a little bit the same. Okay. This one is like this one. You can execute it anywhere in the program, and it just shuts down the program. So exit in C or system.exit in Java exits the program. Okay. So obviously that's going to kill all the threads. Okay. Now, Java does not have a thread exit function. So there's no option to exit a thread with a statement. In Java, the only way to exit a thread is to return from the thread. But since the main method is a void method, you don't really have to return. So you could just comment that out and just then now the closing brace is the return statement. So in Java, I could either exit the program or return from main. Returning from main is not, returning from main is the equivalent of thread exit. Here, it only exits the main thread. It doesn't shut down the program like this one does. So this return shuts down the program. This return just shuts down the thread. Okay. Now, both of them. So what's different is return here means shut down the thread. Return here means shut down the program. In both cases, if you shut down just the thread, the other thread keeps on running. So if you shut down this thread, the other thread keeps on running. If you shut down this thread, the other thread keeps on running. If you really want to exit the program when main ends, then you would use this one. This one would be like this return down here, or this exit here. It would be the equivalent of either of those. Okay, so let's just see that happen. Okay. If I do like this, now I get the orphan thread case. Main will return when it gets to here. It doesn't need a return statement. It'll return when it gets to here. And that will terminate the main thread and leave this thread running. So just compile it and run it and wait about 3 seconds. Okay, there was the thread main, the main thread exiting after 3 seconds, and now the orphan thread just keeps running forever. The orphan thread's in an infinite loop. Okay. Okay. Now, on the other hand, okay, this does exactly the same thing. You know, a return statement on a void function is the same thing as just hitting the closing brace. So this one's just the same thing. This one shuts down the program. Okay, so, but you could call that from anywhere. Any thread can call system.exit and it will shut down the program. So there's nothing special in this case about main. See, anytime someone calls system.exit, it'll shut down the program. That's the same thing in the case of the C1. In the C1, anyone who calls any thread that calls exit will shut down the whole program. The exit function terminates the program. And you can go here. Here's the page for the exit function. Normal process. See, key is process termination, not thread termination. Exit exits the process. So it shuts down the whole program. So no matter what part of your program, no matter what thread calls that function, it'll just terminate. Now, in the case of Java, look up the system class, because exit was a method in the system class. Okay, there's the exit method. Terminates the Java virtual machine. Now, they don't say process, but it shuts down the whole Java virtual machine. Okay, I mean, that is the process. But instead of saying shut down the process, Java thinks in terms of, C thinks in terms of processes. Java thinks in terms of an instance of the Java virtual machine, which is, if you look it up in Windows Task Manager, every instance of the Java virtual machine is a process. Okay, so this exit function is equivalent to this exit function. It just shuts down the whole program. Okay, but the difference is in C, returning from main is equivalent to exiting the program. In Java, returning from main is just, well, returning from main in Java is like a thread exit. Okay, returning from main in Java just exits the thread. It's just like any other thread. When the thread gets to its return statement, like here, this is the return statement for this thread. If I wanted to, I could put a return statement here. It doesn't need to be there because it's a void function. Okay, and also this is an infinite loop, so it'll never get to there. But this return, just like this return, will cause that thread to terminate. Okay, but if if this thread ever executed exit, then it would terminate the whole program. Okay, so you can get in, at least in both P threads and in Java threads, you can have an orphan thread. The thread that creates the thread can die, and the child thread can keep on running. Okay, so there really isn't, we actually don't even refer to them as parent and child. They don't have a parent-child relationship like processes do. Processes have a parent-child relationship, but threads don't. So from the point of view of Java, all the threads are equivalent. Any one of them can die, and it's not going to take any other threads with it. P threads are also that way. If any one thread dies, it doesn't take any other threads with it. The funny thing is that the main thread, because of the legacy of the design of the C language, the main thread has this role of being, I shut down the program. But that was a quirk of the design of C. It was designed before threads existed. If you were redesigning C now, you probably would make it like Java. If the main function returns, it just returns its own thread and leaves any other threads running. But when C was invented, there was no notion of threads. So it made sense to say that when the main function returns, the program ends. That was just how you shut the program down. Okay, so C's got this quirk that returning from main shuts everything down. In Java, returning from main only shuts down the main thread and leaves other threads running. Okay, I don't know if, I know that there's thread libraries out there where the main thread shuts down other threads, but they probably don't. Right now, there's only 3 thread libraries. Let's see. So right now, there are 4 thread libraries that people commonly use. There's the Windows thread library, the Linux thread library. That's P threads. It's also the Linux thread library. There's the C++ thread library and the Java thread library. So Java has its own thread library. C++ now has its own thread library. Then Windows has a thread library and Linux has a thread library.
What about the .NET framework? Does that have its own thread library?
Yeah, you're right. That would be a 5th one. You're right. That would be because it's just like Java. It's its own virtual machine. And now the Java thread library has to be written in terms of either the Windows or the Linux thread library. So in a sense, you could say there's only 2 really thread libraries, Windows threads and Linux threads. But Java threads act differently enough than Windows threads that we think of its own thread library. So yeah, C# would be pretty much. Now you could also then say there's a lot more, because you could also say that Go has its own thread library. You could say that Rust has its own thread library. So it would actually be true that in that case, you could go on and say that many of the modern programming languages actually do have their own thread libraries. So Rust has its own thread library. Go has its own thread library. What's another one? Erlang. Erlang's a famous example of a language with a thread library. So yeah, so maybe in one of those, there is the case that if the main thread exits, all the other threads go with it. Maybe one of those is like that. Those are kind of thought of as higher level thread libraries. So like Erlang's thread library is really different than the Java thread library or the C++ thread library or the Linux thread library. The Linux, Windows, Java, C++, and probably the C# one are all kind of low-level thread libraries. And some of the other ones tend to be much more abstract and more elegant. So Erlang, Go, their thread libraries are at a higher level. That Python doesn't have a thread library because Python doesn't have threads, and JavaScript doesn't have a thread library because JavaScript doesn't have threads. So those are quirky languages. They're fairly modern languages, but they don't even have threads. Okay, they're called single-threaded languages. They do not allow threads. Okay, so they're kind of quirks to those 2 languages. Okay, so among the low-level thread libraries, it's pretty much Java, C++, Linux, Windows, and I think C#. But C# is both, actually in Java too now, is both a low-level and a high-level thread library. The original Java was, which is what we're kind of doing right now. The original, when you're working with this thread class, the original thread library in Java is really low level. Then later on, we'll start looking at the modern high level Java thread library, which is really different. So C# is going to be like that too. It's got a real low level thread library that came with the language originally 20 years ago. And since then, they've been building a much higher level thread libraries on top of that. And a lot of people would tell you you don't even need to learn the low level thread library anymore. You can just learn the higher level thread library. And I think it's hard to learn the higher level thread library if you don't know the lower level thread library. I haven't found a good reference that can teach the higher level thread library without you kind of understanding the lower level thread library. But eventually, someday it might get that good. Eventually, someday the higher level thread library might be well designed enough that you don't even need to know, just like you don't need to know assembly language anymore to write C programs or Java programs. Someday you can learn how to write threaded programs without ever knowing anything about the low level thread library, like creating threads, stopping threads, exiting threads, synchronizing threads. That would be a real good goal. That is the goal, is to not have, just like nobody writes assembly language anymore, you'd like to have nobody creating threads anymore either. The only thing that should call to create threads would be compilers. Just like the only thing that writes assembly language anymore are compilers. So it should be compiled code that creates the thread, not code you write. So leave it up to the compiler and the libraries to create the threads. That's the goal. But the libraries that I'm familiar with, even the high level ones, they're not that elegant yet. They're what some people call leaky abstractions. They're trying to say they're a high level abstraction, but a lot of what's below them, if you're not familiar with it, the abstraction doesn't make sense. So the low levels leak up into the high level in a way that people use the phrase a leaky abstraction. This another one of these words you can, if you've never seen that. People talk a lot in computer science about leaky abstractions. Where you've got this abstraction, it's supposed to be hiding details from you, but it doesn't. The details are leaking into the abstraction in ways that can either be confusing or harmful, but the details aren't hidden by the abstraction as well as they should be. Okay, so right now, even the high level thread libraries tend to be a bit on the leaky side. And so the low levels are, and then again, if you're a computer science student, computer scientists should understand the low level foundations of much of this stuff anyway, because somebody has to write the high level stuff. So it's usually considered computer scientists who would be learning the low level things so they understand how the high level things are built on them. Okay. So now let's look at, that's the last example I want to do out of the folder on threads. Okay. So we've got these two folders that duplicate Java threads and P threads, with lots of examples. Pretty much done. Well, let me show you one other example. I'm not going to run it. I'll show you in a second why. I didn't write this in P threads. Probably should have. What happens if you create 100,000 threads? Okay, it's interesting. Not much. Modern computers are pretty efficient. So if you create 100,000 threads that don't do anything, it doesn't really hurt. I don't want to run it on this computer because I'm afraid of clobbering Zoom. I know that when Zoom is running, I'm a little bit afraid of clobbering Zoom. So I'm not going to run the thing that creates 100,000 threads. But on my machine, it only takes a few seconds, and the threads are just created and they die. Now these threads don't do anything. Okay, so it's 100,000 threads that don't do anything. It only takes a few seconds. This version creates the threads as implements runnable. This one creates the threads as instances of the thread class. New thread. Okay, and they run about the same speed, which is also kind of interesting. It's no faster or slower to create the threads this way than it is to create the threads this way. On the other hand, if you let each thread live for even 1 millisecond, so if you comment that makes each thread. Now, what happens here, if you do it this way, you're never going to have 100,000 threads on your machine. because once a thread is created, since it doesn't do anything, the threads they're created and die. So basically, the thread control block data structure is created, and then the thread controls block data structure is deleted because the threads don't do anything. So you're basically having the operating system create 100,000 data structures and then delete 100,000 data structures. And it doesn't seem to skip a beat in doing that. But if you make the threads exist for even 1 millisecond, they hang around for a while. So now you're going to start ending up with tens of thousands of threads. At any given time, there could be tens of thousands of threads in existence. This will bog my machine down for about 5 minutes. The machine will struggle to create 100,000 slowly, very shortly lived threads. They only live for 1 millisecond, but it'll do it. It'll create 100,000 of them. That's interesting because in the old days, creating 100,000 threads was considered a challenge. There was a time when it was this huge, could an operating system possibly create 100,000 threads? That was actually a challenge about 20 years ago. Operating systems, it was a real breakthrough when an operating system could create 100,000 threads. Now, it's not a big deal. If you made these threads last for more than a millisecond, it probably would start becoming a big deal. If you tried to make, I don't know if Windows can create 100,000 threads and have them all running at once. Like right now on this machine, if I go here to Task Manager, this machine is only running 3,000 threads. So it can handle 3,000. I bet it can handle 30,000 threads, maybe, but 100,000 threads, maybe not. If they were really, really long-running threads, they didn't just create and die, create and die, create and die. If you tried to bump that number up to 100,000, I don't know if Windows could handle it. And I wouldn't want to try it on my machine right now. I mean, it's not going to hurt your machine. In the worst case, you just have to power it up. If you do bog the operating system down to the point where it can't do anything anymore, you just have to pull the plug on. You just pull the plug on it. Okay, so you can do that to an operating system if you want to, but it will create 100,000 essentially empty threads. So that's why I put it up here. It's going to create 100,000 empty threads. They don't live for very long, and it'll do it if they if you let it. On my machine, it was able to do 100,000 1 millisecond threads. So I think, if I remember right, the number of threads crept up to about 10,000 or so. The actual number of threads running at any given time hit somewhere about 10,000 or something like that. And then that lasted for a while. And then finally they all died away. The machine was okay. But for a while, the machine couldn't really do much. I couldn't use the machine for a few minutes while it was trying to create 100,000 threads. Okay, now that could probably even do that. I didn't think to try this in P threads. We could probably also do this in P threads. My guess is you could create 100,000 P threads just as easily as you create 100,000 Java threads. The Java threads actually are P threads and Java threads both end up being Windows threads. We're running on a Windows operating system. So when we create a Java thread, we're actually creating a Windows thread. Java has to ask the operating system to create a thread for it. Same with the P threads. If you're running P threads on a Linux machine, P threads are Linux threads. But if you're running P threads on a Windows machine, P threads has to ask Windows to create a Windows thread. And if you're curious, in this folder on P threads, there's actually a folder of Windows thread functions. These programs are actually native Windows thread functions. They're not P thread. I stuck them in the folder on P threads, but they're actually not P threads. Those are the equivalent programs written in Windows threads running natively on the Windows operating system. So those thread functions don't ask, they're just talking to the operating system. The P thread functions are talking to the Windows operating system. Then these are actually Linux programs. They're actually the same as the ones in this folder, but I just include one different header in them. But so in a sense, they're not really any different, but they include these pthread functions were meant to run on Windows, so they include Windows.h. So these all include Windows.h, so they won't compile on Linux. So I basically just deleted the windows.h include file, and then these run on Linux. So these files are just these files with windows.h deleted from them. But you can open this folder on Linux, run make, or on Windows subsystem for Linux. So for example, here, what I can do here is run now I'm in Windows subsystem for Linux, and I can just type make, and those files compile as if they were on Linux. If I did that in this folder, these won't compile under Windows subsystem for Linux because they include the windows.h header. So they're not really Linux programs because they include windows.h. So these are Linux programs. Okay, see, they've all been compiled. Okay, so P threads are native Linux threads. P threads on Windows need to ask the Windows operating system to create a native Windows thread for them. These are native Windows threads. Java threads need to ask the Windows operating system to create a native thread for them. So Java threads really every Java thread really is a Windows thread, unless you do, but if you compile these on Linux, then these Java threads become Linux P threads because they'll have to ask the operating system to create threads for them. Threads belong to the operating system. No programming language can create its own threads. Okay, there is no such thing as a programming language that has threads built into it. They just have libraries that ask the operating system to create threads for them. Threads have to belong to the operating system. But if you read the literature, you'll see lots of references to things called lightweight threads, and we'll talk about those later in the semester. There's a notion of something called lightweight threads or green threads, or sometimes called fibers. Instead of using the word thread, they use the word fiber. A fiber is like a different kind of thread. We'll see what those are. Yeah, they're thought of as a different kind of thread. And in a way, they're not, but in a way they are. So if with the right explanation, you can see what people mean by these lightweight threads, green threads, fibers. But the truth is, threads belong to the operating system. So only the operating system can create a thread. Okay. Now let's switch to this folder that does the race conditions in Java. Okay, and let me download the race conditions in P threads too, just for again, the Java race conditions mimic the P thread race conditions. So I just tried to write them kind of in a parallel way. Okay. So this race one in Java is very much like that one there. Okay. Okay. So let's look at the code here. This is the one that has race conditions. So the race conditions aren't solved in this. It's exactly like the one we looked at before. Okay. There's these three counters. There's a flag. One of the counters belongs to one thread. One of the counters belongs to another thread, but one of the counters is shared. That's the one that's going to be the race condition. That counter is shared by the two threads. When the two threads try to share that counter, they clobber it. They step on each other's toes. And we'll go back over again the kinds of things that can happen. Okay, so here's the two thread functions. Each thread function, see, these guys are static variables. Okay, so they're just global variables to this. See, this is a static method. These are not static functions, but they're going to be run as threads. So they're neither instance functions nor static functions. They're threads. Okay, to access, the easiest way to get them to access this global variable was to make it a static variable. In the case of the C program, these are global variables. So they're in the scope of the whole program. Okay, so these threads down here can access these variables as just global variables. Java has no global variables, but in this class, I can put static variables, and these guys sit inside the class, so they have access to the static variables. Okay, and actually everybody has access to the static variables as long as they use. See, I have to use the name of the class, so the variables are. See, the name of the, I have to use the name of the class dot name of the variable because they're static variables. Okay, so and I made them. Well, I made them public, so actually anybody can access them. If I made them private, then only the code in this class could access them. But it doesn't really matter. There's nobody else who's going to be accessing them, so it didn't matter if I made these public or private. Okay, so these are static variables. So I access them by saying name of the class dot variable. Okay, so that's the shared one. So see, that one's grabbed by both of them. Now, here's what you think. 2 threads, 2 CPUs. CPU 1 reads that variable at the same time that CPU 2 reads that variable. So they both read, say, 17. Okay. Now, this variable stores that. Now, this thread stores that variable. Oh, they read 17 and they increment it. Okay. So now think about, that's already quirky. He reads 17 and he reads 17. He increments 17 to 18. But what does he increment? Does he increment 18 to 19 or does he increment 17 to 18? It kind of depends on exactly whether they actually saw the variable at the exact same time or not. It could very well be, what could really happen is he reads 17, he reads 17, he increments 17 to 18 and stores 18. He rereads 17. It depends on how the plus plus is actually implemented. When it comes time to do the plus plus, does this reread the variable or not? Okay, if it rereads the variable, it might reread it now as 18 and increment to 19. If the plus plus doesn't reread the variable, then this would still be a 17 and incremented to 18. But that means that one of these plus pluses got lost because you read this as 17, it was supposedly plus plus, and you read this as 17, supposedly plus plus, but they end up being 18. Okay. Now, another funny thing can happen. In the next line, you go back and read that variable and store it here. Suppose the CPU left this thread right after this thread did this line. Suppose the CPU abandoned this thread to go do something else. Meanwhile, this thread kept looping. This thread would take plus count and increment it up to maybe 117. So this thing could be this CPU could be running inside this thread while this one is halted at line 69. Then when this guy goes back, count is no longer 17 or 18, it's now 117. So this guy sees count jump massively when it just gets from this line to this line. There's actually a whole number of different weird things that can happen. The truth is, there's no reason to think that old count minus new count is going to be just 1. If you read this naively, you take this variable, store its value, then increment it, then take this variable, store its value. This guy should be 1 more than that guy because you took the old value, stored it in here, incremented it, then read it again with the incremented value, stored it in here. So the only difference between those would be 1. New count would be 1 more than old count. And on a single threaded computer, new count would always be 1 more than old count. But because this thing is going to be running on 2 threads, there's no reason to think that they should have different values. But you only get a bingo here where these things differ by 1 if you interrupt these guys at just the right time. It's not the case that it will always cause a problem here. It could very well be that one CPU might execute both of those 2 lines and then go do a printf or go do something else. The other CPU executes those 2 lines in tight, so it could very well be that those 2 lines are always executed together and those 2 lines are always executed together. So even though there's 2 threads, you might get lucky. Actually, given how fast computers execute 2 lines of code, we'll see in a minute that that's actually what you expect. more often than not, the CPU can execute those two lines of code so quickly that another CPU can't interrupt it. So the race condition actually doesn't show up all that often. Okay, let's just compile it and run it and see. Now, if you look, this program ran for, oh, I forgot what it was. About 10 seconds or so. No, yeah, 20 seconds. And it only got a handful of race conditions. Okay. It ran for 20 seconds, only a handful of race conditions. And if I run it, sometimes there'll only be sometimes there'll be a medium number of race conditions. Every once in a while, there'll be next to none, because the race condition only happens when these guys interrupt each other at just the right time. So let's run it a few more times. Okay. Only, there was a small handful of race conditions. There, not very many, again, not too many race conditions. Here, there was a little bit more. Okay. I think every once in a while I've run it and there weren't, oh, there was a whole bunch of race conditions. Okay. So that time I got quite a bit more. What's going on? Well, it's just, see, significantly more race conditions that, compared, that was a few hundred race conditions, probably several hundred, compared to this run, which was just what, 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay. So 8 race conditions compared to hundreds of race conditions. Just the quirk of the scheduler. Somehow here, those threads were stepping in this code in such a way that maybe they somehow ended up really synchronized with each other. One thread was stepping through this code exactly when the other thread was stepping through this code, and they somehow stayed neck and neck with each other by some quirk and got a lot of race conditions. Whereas in this case, the threads were just really out of sync with each other. One thread was doing these two while the other thread was doing something else, and then the other thread was doing these two while the other thread was doing something else, and they never stepped on each other's toes. Okay, so you can't predict race conditions. Okay, it's just impossible to predict race conditions. Now, if you can even make the race conditions even more rare by running this program on just one thread, on one CPU. We did this with P threads too. Oh, these are left over from TextPad. So open a command prompt. Okay. Use Task Manager to make that command prompt be one-threaded by making it, okay, that's the command prompt I'm doing. See, that's the folder I'm in. So that's my CMD. Give it only one CPU. Now, anything that's run on that, from that console, really only gets one CPU. Now run our program on one CPU. And that should end up giving us even less race conditions, because now the only way to, we did this before, the only way to get a race condition is if you switch from one CPU to the other exactly at the end of that line. The only way to get a race condition is, since there's only one CPU and you're either doing this function or you're doing this function, you can't be doing it at the same time because there's only one CPU. The only way to get a race condition is to break between line 69 and 70, or to break between line 89 and 90. So the CPU has to switch from here to here exactly that one spot for there to be a race condition. No race conditions. So the program ran without a race condition. Now, this is why in the old days, people could write sloppy code and get away with it. Because in the old days, when there was only one CPU, you could have race conditions galore in your code and no one would ever notice it. Eventually, we'll hit a race condition. Wow. I'm a lucky fellow. See, if I was a software developer in the 70s or 80s, I'd be getting away with murder now. Yeah. See, so that shows you how rare the race conditions are. I'm not getting any. Now give this guy 2 cores. Give him another core. Now the race conditions come back. Now once you give it 2 cores, it's hard to avoid the race conditions. Not too many, but I get, yeah, and if I give it more cores, I'm not likely to get more race conditions because there's only 2 threads. So giving it more cores isn't going to make it any more likely to have race conditions. Okay. Let me go back to 1 core. Let me give it a different core. The fact that, oh, I remember doing this the other day at home by myself, and I noticed something funny. I think this core is special. I think it was these are hyper threaded. So these are actually the same core. These 2 guys are the same core. And if I remember right, CPU 0 and CPU 1, I think they're treated specially by the operating system. So I think the reason we never saw any race conditions is because those 2 cores seem to be heavily burdened with the operating system. So let's give it just 1 core over here, away from any, like this special thread, this special core. Now I think we're going to see race conditions, even though it's only 1 core. Still not getting race conditions. Now, one day I was getting race conditions on any other core except the first core. The first core was special, but it could also just be something. There's something about my computer right now. Maybe, oh, you know what's different? I'm running a Zoom. Zoom makes things different because Zoom is streaming video all the time. So Zoom really causes a background noise to this that wouldn't be there otherwise. See how every single core is kind of busy, at least a little bit, and overall my computer is 16% in use. That's Zoom. See, if I wasn't running Zoom, most of those cores would be just at 0. But since I'm running Zoom and Zoom is streaming a video all the time now, every core has got a little bit of work to do because Zoom's pretty labor intensive. Zoom's, processing video is pretty labor intensive. So the fact that I'm running Zoom is going to affect these little experiments. When people do these experiments in the real world, like for research purposes, they have to be so careful about how they set up their computers because you can't just do this stuff on a regular computer because you just don't know what background noise is going to affect your results. So here, I'm pretty sure it's Zoom that's changing the behavior. You might try it on home. I have a feeling that, at least when I did this a few days ago, core 0 was different. My memory was that core 0, because I think the operating system mostly uses core 0 for scheduling itself. So core 0 seemed to be always kind of more on the busy side. And then the other cores, if your machine is lightly loaded, the other cores will be not doing anything. And then if you run it with 1 thread, if you run it on 1 core, but the core is real lightly loaded, you might see race conditions because it'll bounce between the 2 threads much more quickly. But if the core's got other work to do, it's not going to bounce between your 2 threads a lot. It's going to bounce from your thread to something else, to this thread, to something else, back to this thread, and it just becomes way less likely for it to just interrupt at the right time. But if it's only doing these 2 threads, there's more likelihood that it could halt right between those 2 lines. So then you'd have to run the 2 threads on 1 core and only those 2 threads on the core. Then you're likely to see a race condition. But if the core's got some other responsibilities, you're just going to bounce from this thread to some other thread, then to this thread, then to some other thread, then back to this thread, then to some other thread, then back to this thread, and you'll never get a race condition like we're seeing here. So Core 0, you might find is less likely to give you a race condition, and the other cores are more likely to. But if you give it 2 cores, you'll see lots of race conditions. Okay. Okay. Now let's see how to, in Java, how to prevent the race condition. Remember, this is what we call a critical section. What we really want to do is say that if 1 core is in here, well, actually, the critical section is lines 69 and 70 combined with lines 89 and 90. The 4 lines together are a critical section. If a core is in one of these pairs, no core should be in the other pair. Okay, so if 1 core is doing this stuff, we don't want another core doing that stuff. So we want to essentially put a lock around these 4 things so that if somebody enters this thing with the lock, it'll prevent anybody else from entering this thing with the lock, but it'll also prevent somebody from entering this guy. Because if this guy's locked, then this guy will be locked. Okay, and we did that in pthreads with a mutex. We wrapped there's the 2 lines that needed to be protected. They're wrapped in this lock, unlock the mutex. So you lock the mutex, okay, and you unlock the mutex. So pthread mutex unlock mutex, pthread mutex lock mutex. The function is called pthread mutex lock. I happen to call the variable mutex. I could have called the variable Bob. That's why they put the name. That's where the redundancy comes in. I didn't have to call this thing mutex. I can call the variable anything I want. So to make the code more readable, they made the function name real explicit. Pthread mutex lock. Okay, pthread mutex unlock. And then then it's assumed that this variable here had the type of a mutex. And it has the type of a mutex. It's created up here. It's declared to be a pthread mutex. It's actually, the type is pthread mutex. And I called the variable mutex. I could have called it anything I want. Could have just called it, I could have called it lock. I could have called it bomb. If I called it lock, then down here you would be saying pthread mutex lock lock. So the naming is whatever you want it to be. The function name's a good name. It's very readable. You're locking a mutex, and this guy is the mutex. And most of the time when people create these things, they call the variable mutex because that's what it is. Okay, now let's look at how Java would do the same thing. Java's got a really quirky way of doing this. And this is one of the reasons why I thought it's easier to do P threads before Java threads, because Java's way of doing this is, well, I think it's kind of hard to explain. Okay, so up here, I've got an object. I called it my stupid lock. Okay, that's my variable name. That's the type it is. The type is object. The type is not lock. The type is object. Turns out that in the Java language, every object is a lock. Okay. They decided that it should be the case in Java that every object is a lock. Okay. And so you just create an object. Now, normally in Java, objects are not very useful because there's not much in an object. But until you get to this level of learning Java, you learn that, one of the few things that are in objects is they are locks. Okay, so objects have very few responsibilities. They have almost no methods in them, but they are locks. Okay, so I create my stupid lock object. Okay, then down here, when I want to lock these 2 lines of code, I call the synchronized. Now, see this notation? Okay, let me. What is this? What is that syntactically?
Statement.
An if statement. What's this guy syntactically?
While statement.
While statement. What's this guy syntactically?
Method.
Well, it might be what?
Statement.
Pardon me? Syntactically, it could be what?
It can be a method.
Yes, a method call, not a method call. Notice that the syntax for these guys is the same. This is not a method, it's a statement. This is a statement. Now, this could be a function call. But the notation for function calls is also a notation. Like now, suppose I put Bob here. What's Bob?
A parameter.
No, that's an if statement. What's Bob?
Condition.
Yeah, a Boolean condition. Same here. Bob must be a Boolean condition. What's Bob here?
It would be a parameter.
Yeah, it'd be a parameter. So this would be a function call with a parameter as opposed to a statement with a, in this case, a Boolean condition. Now, look at this guy here. What is he?
It's a method again.
No, it's not. This is like if and while. It's a keyword in the Java language. This is a synchronized statement. It's not a function call, okay? And you can kind of tell because it's got braces after it. Like if I fit, like here, this gets braces after it. And this gets braces after it. If this is a function call, you don't put braces after it, that would be a syntax error. You would probably put a semicolon after it. Or maybe you might do something like add, like if it, whatever, it depends on what it returns, but it would return something to you, okay? This guy is actually a new kind of statement in the language. That's a while statement. That's an if statement. This is called a synchronized statement, okay? And I should have wrote these a little bit careful. I should have put spaces there. My habit is now, I've developed a habit of putting a space when things, so if I go back over here, I put spaces when they're statements, and I don't put spaces when they're function calls, okay? And I've adopted that, and that's a style that a lot of people use. When things actually are statements, they put a space there. When they're statements, they put a space there. When they're function calls, they don't. I've seen other people put a space there all the time. And I've seen other people who put no space all the time. So they write these the same. I think it's helpful to the eye to put spaces on the statements and put no spaces on the function calls, like because in math you write f of 3. You don't see math books putting a space there like that. That would be real confusing in a math book. That's a function call, and you write the function calls like that. So I should have written this. I should have put a space there, just like, and I should have put a space there. That's a statement, a while statement. That's an if statement. That's a synchronized statement in Java. Synchronized statements are not function calls. Now, see here in C, I'm sorry, over here's the C. See, these are function calls that lock and unlock the mutex. They're part of the pthread library. Those are functions that lock and unlock a variable. In Java, this is not a function in the Java language. This is a statement in the Java language. It's a keyword in the Java language, and it does. Now, this is the thing that does the lock, and then this is the lock. The lock is my stupid object. Okay, so like over here, this thing This is the function that locks that mutex. And this is the function that unlocks that mutex. In Java, this is the statement that locks that object. There is no unlock method. The unlock is the end of that statement. So the unlock happens automatically when you get to the end of that statement. Here you had to explicitly lock, and you had to explicitly lock and then unlock. Okay. Here you wrap the critical section in a synchronized statement. It's not a function. But the quirky thing is it trips a lot of people up, especially if I write it like that. You think, oh, it's just like pthreads. In pthreads, you call the lock method, the lock function on that variable. Okay, so that's a function, that's a parameter. Here, that's not a function, that's not a parameter. That's a statement, and this is just part of the statement. So it's more like if Bob, while Bob. And notice that this has braces after it. This has got braces. See, there's the braces that complete the statement. So it's a synchronized statement. Okay. The synchronized statement takes any object and locks the lock in the object. The lock itself is inside the object, and every object has a lock. So now I made that lock a static variable in this class. So that's how I access it. I say the name of the class dot my stupid lock. Okay. Now, if this thread owns that lock, that would see, now I use the same object down here. The thing that makes these two and these two one critical section is that I'm using the same lock in both of them. If I used one object here and one object here, they wouldn't exclude each other. When one thread entered here, it would own that lock, but when another thread entered here, it would own a different lock. The point is to have these guys share the same lock. So if a thread enters here and owns my stupid lock, then some other thread hits this thing and gets blocked because my stupid lock is locked. Notice you don't use the word lock and you don't use the word mutex. This guy is not a mutex. It's not even a lock. We'll say later on what this thing is. Okay, so it's not a mutex, and you're not really locking it. You're doing something a little bit subtly different. Okay, so Java people say you're synchronizing on this object, but it has the same effect as acting just like this. It acts just like that, where the unlock is the close brace. Okay, so there is no unlock. The unlock is just the close brace. Okay, so it's kind of straightforward. You know, if you just kind of think of any random object, you can use it as a lock. We'll see that you're not supposed to use random object. When you write more sophisticated code, you're supposed to use these objects in a careful way. But you can just, in this case, I'm just using a random object. I just created this. Yeah, that's why I called it my stupid lock, because this is kind of not really the right way to do things. But in this simple program, this stupid lock is acting exactly like this mutex up here. I'm using it exactly like this mutex variable here. Okay, so it's a global variable that is the lock for this program. Okay, but you don't call a lock function, you call the synchronized statement, or I should say you execute the synchronized statement. Executing the synchronized statement, what it mean if no other thread has executed the synchronized statement on that object, then you own the lock on that object and you enter your critical section. If some other thread is currently owning the lock on that object, then if you execute a synchronized statement, you block until that lock has been released by the other thread leaving the synchronized statement. Okay. Two synchronized statements are tied together if they use the same object. Okay. So so these two, this block of code and this block of code are the same critical section because they share this same object. Okay. Now this program, if I compile and run it, won't have any race conditions. Okay, no race conditions. And I'm running it on multiple threads. It doesn't matter how many threads I run it on, there's not going to be any race condition because once one of the CPUs enters into here, the other CPU can't possibly enter into here. Okay. All right. Now, there's another version of this program. If you look in the folder, there's a version 2 of it. I'm going to comment out my stupid lock. That's not going to be my lock anymore. And I'm going to do something really quirky. But you can actually do this in Java. It's probably, I don't know if it's frowned upon or not, but here's what I'm going to do. My lock object is the static class object of this class. Remember, static variables exist. Remember, if you go back to the earlier version, this is a static variable. These are static constants. Where do the static variables live? Well, they actually live in an object called the class object. So the static variables sit in the class object. So the class object is itself an object, and it holds the class variables. So I'm going to use, in this program, the class object as the lock object. I mean, this is like playing games with the Java language. You're allowed to do these things if you once you've learned the language, you're allowed to do this kind of stuff. But most people don't know about these subtleties. The static variables live in the class object, so why not use the class object as my lock? So then I don't need to create this kind of dummy variable. I don't need this. This was like a superfluous variable. It was sitting in the class object to serve the purpose as being a lock. Why do I need it in the class object to be a lock when I could just use the class object itself as the lock? So in a sense, this is just a more efficient version of this guy. So I'm using the class object. The name of the class dot class is the class object. The class object is used for what's usually called reflection. There's a whole notion in Java and several other languages of something called reflection. Is when programs can ask questions about objects. Instead, they don't use the objects to call methods and things like that. They can ask questions of the object. Like you can ask a question like, here's an object in the heap. How many methods are in it? Or here's an object in the heap. Does it have a method called Bob that takes an integer parameter? Does this object have a field called Sally? So reflection is when you're allowed to ask the Java virtual machine questions about objects in the heap. Okay, so it's one of the more advanced topics in Java, but it lets Java programs, it allows executing Java programs to examine or introspect itself. It doesn't really examine and introspect itself. It examines and introspects itself, its own objects and any other objects. It lets running Java programs ask questions about objects. One of the main tools for doing it is this. One of the tools for doing it is this class object. The class object is where you can find out information about a class. Okay, so it holds the static methods. It also holds some other information, but it is in fact an object in the heap, so you can use it as a lock. So it's just kind of a quirky thing. And I've seen people do that. I've seen code that does this. I've seen people use these class objects as if they were locks. So it is something that people do in their code occasionally. Okay. Now, this program really is essentially equivalent to this one. Again, instead of having this field that's a static field in the class object, I'm just going to say, go ahead and use the class object itself as the lock. Okay, so instead of reaching inside the class object for that, instead of reaching inside the class, look at the difference. Here I reach inside the class to get that object. Here I essentially you can think of this as reaching inside the class to get the class object itself, but the class object itself is the thing that's holding the static object. So in a sense, I'm just using the static object itself instead of reaching inside the static object. Okay, so this is just another stupid lock in a way. Okay, but I get it kind of automatically. Okay, and so if you compile and run this, it won't have any race conditions either. Okay, because it's now we say it's synchronized. We're using synchronized. We're using the synchronized statement. So that's synchronizing this critical section for us. So the synchronized statement is synchronizing, or it's having the effect of being giving us mutual exclusion. We'll see as we do a little bit more of this that the synchronized thing is more powerful than a mutex. It is not equivalent to this mutex over here. Right now I'm using it like a mutex, but the synchronized object is more sophisticated than a mutex. So it wouldn't be fair to say it is a mutex. It's really something a little bit more sophisticated than a mutex. Okay. Okay. But in this case, this simple example uses it as a mutex. Okay. Now let's look at another example from this. Oh, let me see.
Professor, a question.
Yeah, sure.
Does the synchronized statement is used only for this purpose, or it has like it can be used for any other purpose too?
It can be used for a lot of purposes because it's more than a mutex. Now, it's only used for synchronization, but it can be used for more than just a critical section. And it can be used as if it was more, it can be used in a more powerful way than a mutex can. So it's only used to synchronize threads, but it can do more than just this simple kind of synchronization. So I don't know if that's what you mean. It only is it's only used for synchronizing threads, but it can do some pretty sophisticated tricks. Okay. So it's more powerful than a mutex. A mutex can only do mutual exclusion. That's its name. So a mutex can only have the purpose of letting only one CPU into that block of code. That's what a mutex does. It just says only one CPU can be in this block of code at a time. We'll see later that there are more sophisticated things you can do with synchronization. We'll learn more sophisticated kinds of synchronization. The synchronized statement can do a lot. So it can do more than just mutual exclusion. But it's only useful for threads. So if you write a single-threaded program, there's nothing you can do with the synchronized statement. Okay, the synchronized statement is only going to be helpful if you're writing multi-threaded code. So you have to have multiple threads to make use of the synchronized. Okay. Okay, now let's see. Now this is back to unsynchronized. So here's back to a race condition. So if I run this one's back to having race conditions, but it's a little bit different than before. Okay, so this one's unsynchronized, but it's got the synchronized statement in it. Okay, there's the synchronized statement, but it's not working here. Okay, now over here, I synchronized on, oops, let's see. Yeah, done. I synchronized on this object that is the static class object. Here, I'm synchronizing on this. See, and I'm synchronizing on this. Okay, but it didn't work. And the question here is why? Okay, and this is where people get tripped up in Java. They'll think, but you're synchronizing on the same object. You're synchronizing on this object. And the point is, you're not synchronizing on the same object. This guy is an instance of this class. This guy is an instance of this class, they're not the same object. So even though you use the same word here, this and this are not the same this. Okay. This is an instance of this class. This is an instance of this class. So in a sense, this is this thread object. This actually is, no, I'm sorry. This is this runnable object. This is this other runnable object. Then from this runnable object, I create one thread. From this runnable object, I create a different thread. This is not the threads themselves. This is the runnable objects. So this guy implements runnable. Okay. This is the run method in that class. This would be this object. This is the F1, and the other this is the F2. So now what happens here, the reason this doesn't work is this synchronized owns an object. Nobody else can enter their, he's the only thread that can own that object, but this other thread grabs a different object. So even though this looks, see here, I use the same class there is there. So I have the same thing typed there as I have typed there. Okay, that's synchronized. So somebody else will make the mistake of thinking you wrote this here, you wrote this here. So they're thinking on the same object. And this is actually considered, this is like a not uncommon mistake for people to make when they're writing Java threaded code, to get mixed up about what this is. This is from a different thread than this. This is from a different object than this. So this guy's syncing, this guy's locking one object, this guy's locking a different object. So you got to be really careful when you use these statements. Okay. Now, if you go back to the pthread version, this looks a lot like the pthread version. You're calling, you're locking an object, locking that same object, locking that same object. The fact that you're using the same word here, here, the fact you're using the same word means it's the same object. Mutex is that same object. But in Java, the word this has got many meanings, and you got to be really careful when you use the word this. So this, and this are different thises. Okay. So you don't have synchronization in this one. Okay. Now here's another example that's also unsynchronized. Okay. Now again, this one, if you run it, it's going to have race conditions. Whoops. Oh, I went. We're going. Okay, let's just. I forgot to set a timer again, so we're going over time. I just realized we've gone over. But this one's also unsynchronized, but it makes a different mistake. Oh, this one synchronizes the run method. Now, instead of using a synchronized statement, it's using a synchronized method, but it's not working right. It's not doing the right way of synchronizing the method either. Okay, so that's where we'll start later. This is a synchronized keyword on a method. This is a synchronized statement. So Java has two uses of the word synchronized, as a modifier on methods and as a statement. And this is a wrong way to use it as a modifier on methods too. So this doesn't synchronize like you think it would. Okay, so we'll quit here, and we'll pick up with this example, and we'll start talking about what synchronized means here and what synchronized means here, and how you use these things in Java. And their method, this stuff is in the readings too. So in the section, in those readings about Java threads, they talk about the synchronized methods and the synchronized statements. Okay. Like, any question before we quit? We run out of time, but anybody have any questions? Okay, so next week we should be back in the classroom, but I'll use the website to let you know, so it'll say here, I have every reason to think that next Wednesday we'll be back in the classroom because it's probably not going to snow again. So But you know, it'll say here what we're meeting, you know, if we're back in the classroom like we were on Tuesday. Okay, so have a nice weekend.
Thank you.
Bye-bye.
Thank you, Professor. Bye.
Bye.